So let's look at example 1 here. What it's done is it's not formally saying where a max or min has to occur, what property we care about. What it's asking us to do is to investigate. So it says find the value of the derivative at the extrema shown in figure 4.3. So what they're getting at is if you look here on 4.3a, what you see a relative maximum. They give you the function. They want to know what's the value of the derivative there. At b, they give you a relative minimum with that absolute value function at 0, 0. They're asking what's the derivative there. Well, again, that's a sharp corner, so we know the answer to that already. I'm not even going to do the math. I know that the derivative at 0 does not exist. Okay, I know that for sure. All right, and then at c, you see both a maximum and a minimum, and it's asking what's the derivative at those points. So, again, with absolute value of x, part b, I know from the left the slope was -1, from the right the slope was +1. We've done this in a previous section. I know the derivative doesn't exist because it's a sharp corner. I'm not going to do any math there, but let's go ahead and do some math for parts a and b. So parts a and b, let's look at part a. If I look at my function f of x, and I'm going to look at it a little differently. I'm going to distribute the 9, so that would be 9x squared minus 27, and then I'm going to divide each one of those terms by x cubed. Each one of those terms by x cubed. And so if I simplify that, the reason I'm doing this is because there's a single term on bottom, and I don't want to use the quotient rule. What I'm ending up with is 9x to the -1 minus 27x to the -3. Why do I care about that? Because now that makes it easier to find the derivative. I can just use the power rule. The derivative of 9x to the -1 would be -9x to the -2, so I'm going to throw that over x squared. And then you'd have minus 27 times -3. Well, if you do 27 times 3, I'm getting 81, so this would be actually a plus 81 over, well, x to the -3 minus 1 would be -4, so that would be x to the 4th. We need to set this thing equal to 0, or sorry, that's the derivative, and what they wanted us to do was to evaluate it at the given point. So at 3, it's f prime of 3, we're plugging in the number 3, it would be -9 over 3 squared, which would be -1, and then it's plus 81 over 3 to the 4th, 3 to the 4th is 81, so 81 over 1 is also a 1, so I'd have a -1 plus 1, which would give me a derivative value of 0. So what is f prime of 3? It's 0. What is the derivative at a maximum? It is 0. What is the derivative at the minimum in part B? It does not exist. What about part C, where we have the function sine of x? Well, let's find the derivative. The derivative of sine, as you know, is cosine of x. We need to evaluate it at these points, so let's consider it at pi over 2. We would have f prime of pi over 2 would be equal to cosine of pi over 2. And cosine of pi over 2 is 0. And at 3 pi over 2, we'd have f prime of 3 pi over 2, which would be cosine of 3 pi over 2. And again, cosine of 3 pi over 2 is 0. So just from these examples we've been given, it comes back to what we talked about on a previous page. If you notice, if it's a hill or a valley, or even a sharp corner, when you have a maximum or a minimum, your tangent line is horizontal, meaning your derivative is equal to 0, or it's a sharp corner where your derivative is undefined. So it seems like almost always the derivative is equal to 0 or undefined at relative or local extrema. So it says, note in example 1 that each relative extrema, the derivative is either 0 or does not exist. The x values at these special points are called critical numbers. So this is really important because you're going to have see me use it all the time. They call it critical numbers. I usually call it critical values. They're the same thing. So instead of calling them critical numbers, I'm going to call them CVs. That's what you're going to hear me say all the time, is CVs for critical values. That is when are the x values give me a second, the x values where the derivative f prime of x equals 0, or where f prime of x is undefined. This is hugely, hugely important. So I'm going to highlight it. Critical values are the x values where the derivative f prime of x equals 0, or where f prime of x is undefined. Where the derivative is equal to 0 or undefined, that is our critical values. And so here, look at this maximum. This is an example where the derivative wouldn't exist. Here's an example of a maximum where the derivative is 0 because it's a horizontal tangent line. You might remember some of the problems in your homework said find the points where the derivative or where the tangent line is horizontal. This is the whole reason why, is because that was leading us up to finding maximums and minimums. So it says definition of a critical number. It says let f be defined at c. That's really, really important. It does have to be defined at that point. The second thing that it needs to be is equal to 0 or not differentiable, meaning the derivative is undefined. So that's the second thing. That tells me that it is a critical number. So first thing you have to do is make sure it exists at the point. Second thing, the derivative has to be 0 or undefined. If that happens, it's called a critical number. And again, I'm going to call it a CV, a critical value. Okay? Now we come to the big daddy of them. It says the next theorem, if f has a relative maximum or a minimum, it must occur at a critical number. So, how are we going to find maximums or minimums? We're going to find all the critical numbers. How do we find the critical numbers? We find the derivative, we set it equal to 0 or undefined. Not all critical numbers are maximums or minimums, but all maxes and mins are critical numbers. Let me say that again. Not all critical numbers are maximums and minimums, but it does go the other direction. All maximum and minimums must occur at a critical number. So if we have found all the critical numbers, we have found all the potential maximums and minimums.